everyone. Now, in continuation of the previous lectures that we have done for the theory of ADC, today I'll be discussing program for ADC interfacing without using interrupt. Okay. So in the previous lectures, we have reviewed what are the various ADC registers that we have, and what is the role of each register, and what is the bit structure of each register. So now we will be seeing that how to write the program for interfacing of ADC without using interrupt. The first thing is hash include lpc214.header files. That means we are trying to include the header files for lpc214. Then include standard input output files. So these are the header files for the standard input output. Now after that is your include serial.h. That means we are including the serial header files, serial communication header files, because see, in between we are using serial communication in the program, so we need to initialize these header files, so those functions will be automatically called just because we have included this header file over there. Okay, now after that we'll begin the program. So void delay, void is one part, then int main program. So in this main program we have first declared some data types. So first is your data type that we are defining, that is int, and the variable is ADC data. So that is the variable we are defining, because the whatever the result comes after the ADC conversion, it will be stored in this particular variable. The second variable that we have is the voltage, and the data type is float. So this variable will be used for storing the values, and for that we are having data type of character, right? And the named, we have defined an array volt, and the size is 3. So basically this will hold the value, that the actual value of after your analog to digital conversion will be stored in this particular array that is there. After that, as you're already aware, what are the pin select registers, right? So we have pin select 0, pin select 1. So here basically we are using P0 2.28 pin, okay, 0.28 pin as the input pin, right? So we are using this particular pin as the input pin for internal ADC. So this is pin number 0.28, right, which is connected to internal analog to digital converter. How this is pin 0.28? Because see, this is your 4 bits over here, another 4, 8, then you have 12, 16, 20, 24, and 25, 26, 27, and 28. So we are making this 1. So because it's considering it as an input pin. Then we'll initialize the UART, okay, that is universal asynchronous receiver transmitter. A very important part here is that AD0 control register that we have seen in the last PPT lecture that was there. The value of this AD0CR is 0x002104002. So this is a hexadecimal value. Now this is very important to understand why we are taking this particular value here. So let me have explained it over here by drawing the bit structure here. So the 2 value, that means it is 0010, and this 0 means it is 0000. So in this case, this particular bit 1, that means it is these are select pins, right? If you see the bit structure of AD0CR that we have seen in the last lecture, if you remember, then 0 to 7 we have these pins are for select lines. So we are selecting here the ADC pin, which is your 0.1. Okay. Now after that, from 8 to 15 are your clock division pins. Now what does the clock division pin do over here is that here the value we have taken is 04. That means it is 00000100. So this clock division, that means the value 4. So the formula for finding the ADC clock, what is that? PCLK upon clock division plus 1. So PCLK is your peripheral clock, as you already know. So peripheral clock is divided by this value plus 1. That means what is this value? 4. 4 plus 1, 1, and that will be 5. So 15 divided by 5 is 3 megahertz. So what is the ADC clock here? 3 megahertz is the ADC clock. The next bit is your 16 bit, which is your burst bit, right? So this is set to 1 just because we are taking them, considering that into the burst mode for repeated conversions. Okay. Then you have 17, 18, 19 bits. So these are again 0 values that you are having over here. Then again you're having 02, so 0010, okay, and then 0000. So this particular is your 0010, that is for the number of clocks we are defining over here. So this particular bits are defined from the number of clocks. So 0010 gives us the particular value. So after that we have some power down bits, R bits, start bit and edge bits, and some reserved bits. So here in this particular case, what happens that your power down mode bit you have selected, right? The start bits, that is your from your this particular start bits, they are always to be 0, right, in this case, and reserve bits are always taken to 0. You cannot write 1 over here in the reserve bits. This is the way the value has been taken for AD0CR, and that is why this value is there as AD0CR is this value. Now going to the next part, here now what we have is while 1. Now if AD0R1 and hexadecimal value 800000, so why we are ending this here now? Because we want to see the AD0R1. So if you remember, AD0R register, basically the last 31 bit is the done bit. Okay, so done bit, when it becomes 1, that indicates that your conversion is finished and your result is stored. Okay, so how will you identify it here? By ending it with this value. So the moment this particular 31 bit will become 1 over here, you will get as an output as 1. So this is called as end-to-end conversion bit monitoring. This means when the done bit becomes 1, our result is there. Okay, so I hope it is clear. So after that, how you are going to store that value? So in that variable ADC data, now we are going to say AD0R1 and we are going to AND it with 0x000 FFC0. Now why again we are taking FFC0? This is important. So when we say FFC0, so when we say FFC0, actually these are the bits, see, from 0, 1, 2, 3, 4 and 5, and then from 6 to 15. So from 0 to 5, these are reserved bits. So obviously the reserved bits have to be 0. Then we have 6, 7, 8, 9, then 15 tak, this stores, these bits store the result. Okay, so this contains a binary fraction which represents the voltage. Okay, so this is what we want. This is our result, right? So that is why we are ending whatever value comes over here with this particular value, because we want to preserve this result. Now after that we are shifting the data over here right by 6. Okay, so we have to shift this data right by 6. Why? Because we need to take this particular data to the leftmost bit position. Okay, we need to take this at the leftmost bit position, because ADC conversion हमने देखा है that whatever data we have, it should go to the leftmost bit position over here so that it can be used further. So that is why ADC data right shift by 6. Now we want to convert the values of the voltage. So what formula we have? Voltage is ADC data divided by 1023 into 3.3. So this is your formula for the conversion, and resolution has been taken over here. Okay, so from there this formula is coming. String printf volt. Okay, now we want to print the string voltage percentage 1, that means we are having 1 decimal point, and this is the value of voltage we are having. So it will give us the ADC output. So that will be printed, for example, as 1.3 volt, okay, with the 1 decimal point. After that, so all the things we are having, voltage is there. Now we will use UART0 put s put string ADC output. So put the string over here, ADC output kitna hai, then UART0 put s volt. So what is the value of the voltage? That will be printed over here. Now this function will be called because we have included the serial.h header files in the starting, right? So that is automatically this particular function is called from that file. Then after that, delay, give some delay, then void delay void. Now this is just the loop for creating a delay for int ij for I equal to 0, I less than 1000, I plus plus, for j equal to 0, less than 10,000, j plus plus. So this program will give us the result, right? That is how it is going to convert the value from ADC and analog to digital value, and that value is going to be displayed over here.